Very good morning, friends. Today we'll start lecture number 5 on probability topic. Mainly in this lecture we'll be doing conditional probability, multiplication theorem of probability and some theorems in this lecture. Next time we'll continue problems on it. Definition. The symbol PA by B is called conditional probability of under the condition that event B has already occurred, that is already taken place. Similarly, the symbol PB by A is called conditional probability of B under the condition that event A has already occurred or already taken place. The next very important theorem is what? Multiplication theorem of probability. In usual notation, prove that PA by B is what? PA intersection B upon PB. See the proof. This is event A, event B and sample space S respectively. Let A and B be two events of finite sample space S. Let denote intersection of events A and B. Let PA by B denote conditional probability of under the condition that event B has already taken place. Look here. Now it is given that B has already taken place. So this is B. So we have to just focus on it. When B has already taken place, what is A? This is A, this is B. When B has already taken place, A is only this much. So number of elements in A when B has taken place is nothing but this much, which is A intersection B. And since B has taken place, so B will become what? Points in sample space. By definition of conditional probability, P by B is what? This is probability of event A under the condition that B has already taken place. As shown earlier, number of elements in A will be what? A intersection B. This is what number of elements of A when B has already taken place. Since B has taken place, so NB will become what? Points in sample space. Divide both numerator and denominator by NS. N A intersection B upon NS divided by NB upon NS. Dividing both numerator and denominator by NS. Now numerator will become P by A intersection B upon PB. Why this is called multiplication theorem? We will keep answering this form only. This is called multiplication theorem because PA intersection B will be what? PA by B into PB. This is known as multiplication theorem of probability. Similarly, we can prove P by A is what? PA intersection B upon PA. Next heading is what? Independent events. Two events A and B of finite sample space S are said to be independent if occurrence or non-occurrence of one event does not affect probability of other event. Out of the two events A and B, whether one event is occurring or not occurring, that will not affect probability of other event. Then we say that A and B are independent events. It is just like whether a student is present, a particular student is present or not. Teacher's teaching is what? Unaffected. Then teacher's teaching is what? Independent of presence or absence of any particular student. So exactly same way this. In other words, event A is independent of event B if probability of A by B, this is conditional probability of A under the condition that B has taken place. Whether B is taking place or not taking place, it should not affect probability of A. So this remains PA, then we say that A and B are independent. Similarly, event B is independent of event A if PB by A is same as PB. That is, conditional probability of B is same as actual probability of B, then condition is unaffected. If A and B are independent events, then prove that PA intersection B is what? PA into PB. Since A and B are independent events, therefore PA by B is what? PA. This is equation number 1. By definition of conditional probability, PA by B is what? PA intersection B upon PB. Equation 2. From 1 and 2 we get left hand sides of both the equations are same, so right hand side will also be equal. So PA intersection B upon PB is equal to PA. Therefore PA intersection B is what? PA into PB. Hence, if A and B are independent events, then PA intersection B is what? PA into PB. If A is independent of B, then prove that B is also independent of A. Since A is independent of B, therefore PA by B is what? Equal to PA. By definition of conditional probability, PA by B is what? PA intersection B upon PB. Equation 2. From 1 and 2 we get PA intersection B upon PB is equal to PA. So PA intersection B is what? PA into PB. Equation 3. To prove that B is also independent of A, independent of A, consider probability of B by A. Probability of A intersection B upon PA by definition of conditional probability. But from equation number 3, this is what? PA into PB upon PB. PB will get cancelled. Sorry, this is, oh, I did mistake. Upon PA. PA will get cancelled, get PB. So probability of B by A is same as PB. This implies B is also independent of A. So whenever A is independent of B, then B is also independent of A. Prove that two independent events cannot be mutually exclusive. Many students think that when events are independent, they should not have any common point. But there must be some common point. Because a person who is walking on the street, whom I don't know, the question of dependency or independency doesn't arise. So dependency or independency arises when some norms are common. That means they know each other. So here also they should have some common points. Let us prove this. Since let A and B be two independent events, therefore PA intersection B will be what? PA into PB. Since PA cannot be 0. If PA becomes 0, then A will be empty. That means A is what? Impossible event. Therefore PA cannot be 0 and PB also cannot be 0. So their product cannot be 0. PA into PB cannot be 0. So PA into PB cannot be 0 means PA intersection B cannot be 0. If PA intersection B is 0, then A intersection B will be empty. And PA intersection B is non-zero. This implies A intersection B cannot be empty. If A intersection B is empty, then A and B are mutually exclusive, not empty. So A and B cannot be mutually exclusive. Next is, if A and B are independent events, then prove that A dash and B dash are also independent, A and B dash are also independent, A dash and B are also independent. See the proof. Since A and B are independent events, therefore PA intersection B is what? PA into PB. Equation number 1. To prove that A dash and B dash are also independent, consider probability of A dash intersection B dash. Now we apply De Morgan's law. This is A union B common dash by De Morgan's law. Which is 1 minus probability of A union B. Since probability of X complement is what? 1 minus Px, which is 1 minus PA union B is what? PA plus PB minus PA intersection B. 1 minus PA minus PB plus PA into PB, reason from 1. 1 minus PA write in one bracket, minus PB common, 1 minus PA. Now 1 minus PA common, so in bracket you will get 1 minus PB. One minus PA is what? PA complement into PB complement. Therefore, PA dash intersection B dash is what? PA dash into PB dash. This implies A dash and B dash are also independent events. Second part is what? To prove that A and B dash are also independent. Consider probability of A intersection B dash PA minus PA intersection B. PA minus PA into PB from 1. PA common, 1 minus PB, and 1 minus PB is what? PB complement. This implies A and B dash are also independent. And third part is what? To prove that A dash and B are also independent. Consider probability of, in this case B has no complement, so from probability of B we'll subtract probability of A intersection B. So probability of B minus PA into PB from 1. PB common, PB into PA complement. Therefore, this implies A dash and B are also independent. Thank you very much. In the next video, we'll continue problems on conditional probability.